Okay, so I guess we have seen the procedure for drawing the root locus in general, and for this example specifically, right? And I showed you the rlocus command in MATLAB, which is this one here. So you can use the command rlocus or num and denum equivalently instead of just a system that is defined by a transfer function or by the state space. You can directly use the command rlocus of num and denum, or you can even use the command rlocus of A, B, C, and D, where A, B, C, D are the fundamental matrices in the state space representation. So we have seen that. Now we have to look at a couple of more things before we can continue this example. So we have drawn, fine. We know for what ranges of k, which was between 0 to 20, the system is stable, right? Okay, so we say the system is conditionally stable. Condition on what? On the value of k. Now this is asking for more. It says, for what ranges of k does the system show an underdamped or overdamped behavior? And then what value of k puts the complex conjugate closed loop poles at a real value of negative 0.5. So it has not provided their complex parts. It just says the real part of these complex poles is at negative 0.5. Right now, you know that they are at negative 2, right? The poles are at negative 2 plus and minus I. So it says, how is it that we can move them a little closer to the imaginary axis, basically making the system slower instead of faster. So in order to do that, we need to know something here called the location of constant damping ratios and constant natural frequencies. So if we go back to the discussions we had in the past, and if you remember, in general, if we show a pole of the transfer function by sigma plus omega d times I, if you remember, look at this picture, right? So the real part of the pole, we show it by sigma, and the imaginary part of it we show by omega d, and the angle formed by this pole, the vector between the pole and origin, we call it phi with respect to, of course, negative here, the real axis. Then, if you still remember, sigma was what? Let's see if anybody remembers. Yes, it was zeta omega n, and omega d, the damped natural frequency, was omega n times square root 1 minus zeta squared, right? Now, what is omega n? Clearly, let's see, omega n is the magnitude of that vector. Is that correct? I mean, like the component of that vector are, one of them one of them is sigma omega n, the other one is omega n times the square root 1 minus sigma squared. So if I square these, right, if I square sigma and omega d and add them together, what happens? This one becomes omega n squared sigma zeta squared. This one becomes omega n squared 1 minus zeta squared. And when I add them together, I simply would get what? Yes, omega n squared. And when I take the square root of that, then this hypotenuse, of course, is omega n. So omega n is the distance from the pole to the origin. And what is zeta? How can I find zeta? Well, if I look at the cosine of this angle phi, what is cosine of phi? So I'm showing them here for you. That sigma is this, omega n is that, and if I combine, omega n is just the magnitude of the distance, and sigma is what? Zeta is what? Zeta, clearly from this definition, if you look, zeta is I guess here there is a typo that I need to fix. So zeta is sigma divided by omega n, right? If I know sigma, right? And I can do something better than this notation. So let me make it a little cleaner and better for you to make life easier. Okay, so here I'll clean this also for you and use the same thing that I had. So it's easier to understand it. Okay, so now if we go back, sigma is omega n zeta, omega d is omega n square root minus 1 minus zeta squared. So omega n is simply the size, and I can even, if you want, I can take the square root here to make it closer. So they are the same thing. I'm not typing new formulas, but I'm just trying to make them closer to the notation that we have, or the formulas that we have that are more familiar to you. So omega n is the radius of the circle, loci is a circle, I can call it, and then zeta, clearly from here, from this definition, zeta is sigma divided by omega n. And what is sigma divided by omega n? Yes, again, if I form this triangle here, so if I go down right here, and that is sigma, clearly sigma, which is the adjacent, divided by omega n, which is the hypotenuse, is what? Cosine of phi. So what does it mean? When I say omega n is constant, so here I'm looking at the loci or locus, the locations in the complex plane that indicate a constant omega, right? So what is constant omega? Constant omega means the locations that this radius, this distance from the poles to the origin is constant. And what is that? Of course, yes, if this omega n, this radius is constant, then the location for constant omegas will be what? Will be a bunch of circles all centered at origin, and the radius of them is, of course, the constant omega, right? So the constant omega location means what? Means concentric circles, right? That's omega n equal 1, radius 1, omega n equal 0.5, omega n equal 2, omega n equal 3, and so on and so forth. So they are all circles in the complex plane. And what about zeta? When zeta is constant, it means cosine of phi is constant. And cosine of phi constant means phi is constant. And what does it mean, phi constant? When phi is this angle and phi is constant, it means a line with what? With a constant slope, right? For example, if zeta, let's say, is equal to 0.5, so I say, what is the locus of zeta equal 0.5? Well, what angle has cosine equal to 0.5? We know that this angle should be what? Yes, 60 degrees. So the one for which the angle is 60 degrees, this one here, this angle is 60 degrees. With respect to the negative real axis, this line here is the location of what? This is zeta equal 0.5, but not only positive 6, it can also be what? Yes, negative 60 degrees has cosine equal to half too. So that's what this one says. Okay, so this one is also 60, but since it's the opposite direction, I call it negative 60 degrees. So if I put everything back together again, constant zeta in the complex plane means lines with fixed slopes for which the cosine of the angle is equal to that constant zeta. Constant omegas are circles centered at origin with radius equal to what? That constant omega n. Okay, why are these important? Because if we go back and look at this example, what is the example is asking? So this is a little different, but many times we'll see, in this case, it's different. We need the location of constant sigma, which is going to be a vertical line. But many times it says, find the value of K that will set the damping ratio of the system at just some number, let's say 0.5, right? So for what value of K the system will exhibit a behavior, a damping ratio of 0.5, or for what K value the system will show what? In the natural frequency of maybe 2 radians per second. Okay, so it says for what K values I can get any of these. And that's where not only you have to have the root locus of the system, you also need to draw what? The loci for constant omega or constant zeta. And then let's say here, for example, if I want a constant zeta of 0.5, we learned that it's aligned with angle of 60 degrees. So what I do is I draw a line here. Let me make this thicker for you so that you can see. So I draw a line like this with angle 60 degrees, something like that. And this one, because that's also the same thing, right? That's just negative 60. And wherever they hit each other, which is, of course, here and what? Here, those poles are the poles that have a zeta equal 0.5. But what is the K value for them? If I put my poles here, it's 0. But when I move them from the pole and move them to here and from here to here, what K value corresponds to those points? And I'll show you in a second how to find the K value at any arbitrary point, both on the paper and in MATLAB. Okay, so that's the nature. At what K value I can move my dominant poles from the starting points to these points or any other points, and then change the behavior of the system. So that's the nature of this Root-Lucas method. So we learned that the locations for constant omega and constant zeta are what? Now sometimes, as in this example, somebody says, what K corresponds to a sigma equal this or some omega equal to something. So what if somebody asks for those? So let me draw all of them in one place for you just as a reference. So here, so this is one, and let's see, oh, this is another. Good. And if I have a circle with a constant radius like this. Okay, so if I have a circle centered at origin with a radius equal to omega n, that's the locus of constant omega n. Okay, so this is omega n equal to some number, let's say C1, right? Or let's not call it C1, let's just call it constant. So locus of constant omegas is what? Circle centered at origin with radius omega. Locus of constant zetas are what? Yes, we know it. It is, oh, it is a line, right? So if you have a line, that is constant omega, constant zeta. But how much of zeta? Zeta relates to what of this line? We learned that if this line corresponds to zeta, then cosine of this angle, so if this angle is phi, cosine of phi is zeta. So this angle is equal to what? Yes, it's cosine inverse of that zeta, which is a constant. So if I get cosine inverse of the constant zeta that is given, the cosine inverse of that is this angle. So that's a locus of constant zeta. But now, as I said, sometimes it says, what is the locus of constant sigma? So for constant sigma, as I said, it is going to be a what? Yeah, it's a vertical line, something like this. Right? So that value here for the whole vertical line, this is what? Sigma equal a constant, right? So sigma is the real part of the complex. So anything on this line has the same constant sigma. And what if somebody says, what is the root locus for constant omega d? The damp frequency, yes, because omega d is the imaginary part. So what is it? Yes, it is a horizontal line, and this value here is what? Omega d equal some constant. So any point on this line has a constant value of omega d. So these are the different types of specifications that somebody might give you when they are asking for control design. So that is one thing. The other thing I wanted to mention is how to find decay at any arbitrary location, right? So that is very important. So if I come back here, or maybe let me draw it somewhere else to make it a little nicer for you. So let's say in the case of this example, let's follow this example here. So this example says, well, you have a root locus, and the root locus, if you remember, it is this guy here, right? And I want to know if I bring my dominant pole to this point there, how much is going to be my k at that point. So let's do it. Let's take a look together. So I redraw that here. I'll try to rewrite over here for you. So one of them was like coming from here, going to this point, and then following this asymptote, basically. So it was one of the branches in this direction. The other one was something from this point. Let's make it a little less thick. So it was from a corresponding point up here, right? That comes and goes like this, right? So you can see it over here too. It's this green one, and then goes all the way back to negative infinity here. That is the other one, starting from here. And the last one, if I draw it in black, it started from this point and then went to the opposite asymptote, right? So these are the three branches of the root locus. And now the problem says, I want sigma of the system to be at negative 0.5. So what were these numbers, if you remember them? This number here was what? It was negative 2, correct? Because they were at negative 2 and 1. So where was this? We had two breakaway points. One of them was negative 1, if I'm not mistaken. And the other one was negative 1 point something, right? 1.5 or so. So let's find it. So negative 5 over 3 and negative 1, right? Negative 5 over 3 and negative 1. So this guy here is negative 5 over 3. Now what this problem is asking is, I want a sigma of negative 0.5. So bring the poles for me here. Okay, I want the poles to be here. But before that, let me clean this up and move it somewhere else. So I want the poles to be here. here? Let's move it a little bit inward. Maybe, oh, not that much. Can I use mouse? No. Okay, maybe that, and then again, this point here is negative 0.5, and this point here is negative 1. So what we are really looking after is these 2 points. We are looking for these 2 points, okay? The dominant poles, the new dominant poles. And the question is, what is K at these 2 points, correct? So what is K over there? So how do we tackle this problem? We know that any point on the root locus has always this condition that, what? Magnitude of GH at any arbitrary point on the root locus should be equal to what? To 1. Yes, that was the condition. So we always use the magnitude condition, and using that we can find K at any point of interest. Okay, so let's do it. So what is GH in this case? The GH in this case is magnitude of K times what? So we can go back and look. For our case, GH is, no, that one, this one. K over S times S squared plus 4S plus 5, right? So K over S times S squared plus 4S plus 5 at any location should be equal to 1. Okay, now the location I'm interested in is this guy here. Let's just look at one of them, doesn't matter. So I look at this point, I call that point point S, the point of interest. The first thing is, what is the coordinate of that? Can I find it? And that's where I need to do some calculations. So it has a real part and it has what? Some imaginary parts. But what are they? The real part is clear because it lies on the line with constant sigma of what? Negative 0.5. So the real component is negative 0.5, not hard. What about the imaginary part? How big is this distance here from here to here? How much is that? Do you have any guess? What would you say? So if you have MATLAB, of course, you can just, I'll show you, click on that point and MATLAB will give you everything that you need. But if somebody says do it on a piece of paper, how can we do that? And in order to answer that, maybe that asymptote that we have, maybe it can come to play. That's one way, although this point is not exactly on the asymptote. So do you have any guess? What do you think we can do to get this going, right? Because we need omega. And how can we find omega? So okay, let's continue. So as you guess, probably, when I ask some question a couple of times, it means, yeah, that question is not trivial, probably, right? So how do we find omega if we don't have our friend MATLAB? It's not as easy. So you need to do a bunch of complex numbers here. So let's assume that this omega that we are interested in, we call it omega, just the unknown omega, okay? So here we don't know the value of omega and we also do not know the value of k. But we know that at this point, negative 0.5 plus omega I, the magnitude of GH should be equal to 1, and one more condition, the phase condition. So if I knew exactly S, everything about it, real and imaginary part, then I just use the magnitude condition and it would give me K. But the problem here is I don't know all about this location. I don't know omega, so I need to bring in one more equation to solve for the second unknown, and that is where the phase equation comes from. But let's make it a little smaller so that we can squeeze everything in. So what is the magnitude? We know that the magnitude of a ratio of complex number is what? The magnitude of the numerator divided by the magnitudes of terms in the denominator, that is equal to 1. So that's magnitude of k. Of course, it's a scalar, it's going to be k. What is magnitude of, so it's going to be magnitude of s divided by magnitude of s squared plus 4s plus 5. This should be 1 at what s, of course? At s equals negative 0.5 plus omega I. Okay, let's continue. So, if we continue, what is magnitude of this complex number? Yes, it's the square root, real part squared plus imaginary part squared. So it is going to be square root of 0.5 squared, right, which is 0.25 plus omega squared. That's the magnitude of s. This thing, and if we cross multiply, so we cross multiply these guys by 1, times the square root of the other term, which is this quadratic term, this thing times 1 is equal to k. Now, what is the magnitude of the second term, the quadratic term, at that s? Well, we have to first plug that s in and simplify it. If you plug in and simplify, what would you get? So first we have to square this guy. If we square it, you're going to get what? You're going to get 0.25, right? Plus omega squared I squared minus 2 times omega I times 0.5, so it's negative omega I. So that's the s squared term only. Now plus 4 times s. So 4 times negative 5 is negative 2. And that is going to be 4 omega I, and then plus 5. So this whole thing here is that quadratic term. And then we simplified further. So knowing that omega squared is, I squared is simply what? Negative 1. So now the real part will be what? 0.25 negative omega squared minus 2 plus 5. So 5 and 2, that's 3. 3.25. So it is going to be 3.25 minus omega squared, that is the real part, plus I times, what is the imaginary part? So it's a 4 omega I minus 1 omega I, so it's going to be 3 times omega I. Okay, so this guy here is the imaginary part of that. And now what is the magnitude of this whole thing? Of course, it is the real part squared, so 3.25 minus omega squared, the whole thing squared, plus the imaginary part, 3 omega squared, right? So if we do that, now this is our first equation. This is what I call equation number 1. Again, if I knew omega, it was enough to just plug omega into this equation, and that would give me k at that location. But I don't know omega, so I have to resort to the second equation I have. And the second equation says phase of this guy here, k over s times s squared plus 4s plus 5. At that location is equal to what? Plus minus 2k plus 1 times pi, and again this k is the small k, which could only be what? 0, 1, 2, and 3 in this problem. Now, if we just go with one of them here, let's say 0, so if I plug in 0 here, then this angle will be positive or negative pi. They are the same thing. So let's just use k equals 0 and use angle pi. So the angle of this guy should be pi. Now what is the angle? So the angle of a rational is angle of numerators minus angle of denominators. Now numerator is just a constant k, it doesn't have angle, fine. So minus the angle of the denominators. So the first one is s. What is the angle of s? If you look at s, s is this guy here, and the angle is always what? Tangent inverse of imaginary part over real part. So it is going to be tangent inverse of, there's something going on here with this pen. So it's tangent inverse of imaginary part, which is omega. Oh, it's doing something. Let's see what it is. Omega, wow. Something going on here. Let me see. Okay. Type of omega over negative 0.5. That is the angle of the s term. And then the angle of the quadratic term is this one. So angle of that again is tangent inverse of imaginary over real. So it is going to be negative tangent inverse of 3 omega divided by 3.25 minus omega squared. This whole thing should be equal to what? To pi. So that is my second equation. And from the bottom equation, first I have to solve for omega, and then I have to plug it back into equation 1 to solve for what? K. So as I said, you have to be really good at complex numbers if you want to find that without MATLAB. And now one question you might ask is, how do I solve even this equation number 2? That doesn't look like a simple, nice linear equation, and the answer is no, it is not. So in order to do that, what you need to do is, let's see, I can make this guy a little smaller. And what I need to do in order to solve this equation is, I take tangent from both sides of the equation. And if you don't mind, first I multiply both sides by a negative. So I make this negative and I make these two guys positive. And then I call the first term A and I call the second term B. So this is A plus B equal negative pi. Now when I take tangent, it is going to be tangent of A plus B is equal to tangent of negative pi. And we know tangent of negative pi is what? 0, right? Because it's sine over cosine, and sine of negative pi is 0, cosine of it is positive 1, or negative 1, I'm sorry. So tangent of that is 0. Now, what is tangent of A plus B? Here, you need to know trigonometry. So we know tangent of A plus B is what? Tangent A plus tangent B divided by 1 minus tangent A times tangent B. If you forgot that, please keep that in mind. This term has to be equal to 0. That's the expansion of tangent of A plus B from trigonometry. So this term has to be 0. Now, when something like this is 0, it means what? It means the numerator has to be 0, right? So from here, tangent of A plus tangent of B is equal to 0. But you might wonder, why did I take tangent from both sides in the first place? The reason is when I take tangent of A, what happens? Since A has a tangent inverse in it, I'm taking tangent of tangent inverse. So these two functions that are inverse of each other would cancel out. So tangent of tangent inverse would cancel. You're going to be down to what? Just negative omega over 0.5, right? So this is going to be what? Omega over negative 0.5. That's the tangent of the first one. And then tangent of the second one is, of course, the term inside. So 3 omega over 3.25 minus omega squared. This is equal to 0. And now I don't think that is the hardest problem to solve, right? Because all you need to do is to take a common denominator like this. And so it is going to be 3.25 omega minus omega cubed minus 1.5 omega. This whole thing is equal to 0. And again, the numerator should be 0. Therefore, if you factor out omega from there, you can simplify 1.5 and 3.25. So you're going to get 1.75, right? So you're going to get omega times 1.75 minus omega squared is equal to 0. And of course, now your solutions are omega is 0 or omega is plus or minus square root 1.75. Clearly, if you go back and look at that picture again, omega was clearly a positive number. And so the only solution that is acceptable is this guy here. Square root 1.75, which if we calculate it, it is 1.323, 1.323. Okay, so the answer is 1.323 radians per second. That is the omega that I have, 1.323, and then I come back all the way to here, and I plug in for omega to be 1.323 here, and then that will give me the omega at that point. And let's do that. So square root of that. So I say omega, let's use W instead, is equal to answer. And now I'm looking at the square root of something times square root of something else, right? Where the first something is 0.25 plus omega squared. And the second term has 2 squares in it. So it's like this. Right? When this term is 3.25 minus omega squared, if I'm not mistaken, and the other one is 3 omega. So this one is 3 times omega, and that is 7.069. So 7.069. That is the gain that you need at that point. And clearly, you know, this number is between what? 0 to 20. So the system is stable at this gain, but if I choose it that much, it gives me a sigma of negative 0.5 for the complex poles of the closed loop transfer function. And I could also find omega, but as I said, you have to do a bunch of complex numbers in order to get it. Now in MATLAB, life is quite easier, of course. You click on a point and it gives it to you, but it doesn't do magic. It does exactly what I did here. Okay, but let me show you how you can do it in MATLAB. And I mentioned that in here. So you learn that with the Locus command, you can plot it. Now, if you want to overlay on the top of the root locus a range for constant sigma, zeta, or omega, the command is called sgrid. I can show you that. Let me just show you that very fast. So this was the R locus, right? This is the root locus. Now, if I need, in this example I don't, but if I need to add the locus of some omega values and some zeta, let's say just some omega values of what? From like 0.51 and 2 and some zetas, which are like 0.2, 0.5, and 0.8, right? So all I need to do is to pass this command sgrid. So this is what I do. I say the zeta range, I want it to be 0.2, 0.5, and 0.8, and the omega range, I want it 0.5, 1, and 2. Let's see. So if we do that, now that's what we have, right? You see the circles, of course, because the aspect ratio is not correct, they look like ellipse, but they are not, they are circles. So these are the circles for the 3 omegas, and these are the 3 lines and their counterparts for what? For constant omegas of 0.2, 0.5, and 0.8. Now, if, let's say, the problem asks, hey, for what k value I can get a zeta of 0.5, right? So I'm looking at where the root locus is intersecting the locus of zeta equal 0.5. So I'm interested in that point. Can I find the value of that point? Where is it? And then how much is k at that point? Yes. It's really easy. All I need to do is to use the command rlookfind. Okay, rlookfind is going to give me anything that I want. Another way is, instead of this command that I'll show you in a second, I can directly use the data cursor. Okay, and that one is quite a useful tool too. So it's called adding data tip. So let's see if I can add data. So I click here, right click in the blank area and say add data. Oh no, not add data, it's called data tip. Let's see if I can, if it's not here, then I can find it from over here. If not, I can go under tools and see if I can find here, data tips. Let's see if this one gives me what I need. So here, now if I move right at, and I can zoom in if I want to get it to where I want it to be, that's the place that I want to be. And all I need to do is to click at that point. So data tip, go right there and click. And there we go. Clearly you can see that the location is negative 0.628 plus 1.08i. So that's your sigma, that's your omega d. The value gain at that point is what? 4.27. And the damping ratio for that point is, you click quite nicely, 0.503, which is almost a 0.5. And you can always what? Move this point around. Of course, it jumps because you have only so many points on it. But this is the closest that I could get. And you see the gain is around 4.27. Now, if I get back here and look at this problem that I was interested in, this problem says find it so that sigma is equal negative 0.5. So I should click somewhere that makes sigma around negative 0.5. So if I go back here, and let's say if I can draw a line, a vertical line that passes through negative 0.5. Which in this case it's right here, right? I have a 0.5 here, omega of 0.5. So that's this line here is the locus of sigma equal negative 0.5. So where is it that I'm interested? Yes, that point, right? If I can move it over that point, that's where I want it to be. And let's say if I can grab this point, I can grab this data tip point. Come on, please move. Yes, so I can move it all around and get it what? As close as possible to that point. It's quite close. And you see that, you see sigma is close to negative 0.5. Again, you only have a limited resolution here. But yeah, the bad thing is when you have a line, if you zoom in, it's gonna mess up the line. So I don't recommend you zoom on the line. But if you can, grab this point again and get it as close as possible. Okay, no, thank you. Okay, data tip. And I wanted to move this point, move it almost there, right? That was the closest. So you see I'm very close to it. If I move it a little bit on this side, I'm gonna pass sigma of negative 0.5. So it's somewhere between these two numbers, right? In these two. Between 6.28 gain and 5.52. It's very close to 6.28. And if you remember, what number did we find? Was 7 something, right? 7.069. And that is right. Okay, so clearly you can see that it's almost there. Okay, so that's how you do it in MATLAB, by just clicking, and for the sake of quiz, homework, or exam, an approximate is good enough as long as it's close enough. I'm okay with that, but you can get you can use rlogfind too. So let me show you. If you just use this command rlogfind, that is also a good command which does something similar. So I say I want rlogfind of numerator, which in this case was 1, and denominator, which was s times s squared plus 4s squared plus 5s, and then 0 for constant. So if you do that, well, you have to wait. Does not show it, so I assume if ideally it should draw it and let you choose a point, but it doesn't apparently. So I assume you have to first do rlocus to have that graphic in, and then use the command rlogfind so that you can click on an actual point. So here you see I can click anywhere that I want. Of course I need to know where I should click. And at the moment I did not really know, because I need to know where sigma of 0.5 is, and I don't have a command for that. So the best thing I can do is if I can get somewhere close to negative 0.5. So you see this pole is at negative there. I can even move up and get it close to negative 0.5, as close as I can. Something like that. Okay, negative 0.5, 132, and the gain is 601. Now let's see if we found the same thing. So we found omega to be 132, so we found it exactly. That is good. But the k, I guess we made some mistake in calculating k, because the k I found is 7.1 if you make it to 2 digits, but the number MATLAB is giving me is 6.01. So for some reason I made a numerical mistake here. Okay, so I don't know what happened, but This is not 701, it's 601. Okay, that's the gain at that point, but again, the omega that we found is correct. It's 132, and you see MATLAB is giving us 132, right, at that point. So MATLAB here can give you, in this case, quite nice accuracy. Sometimes like this. I didn't do data tip, I just clicked on it directly. So I did not click on data tip. Because when you do data tip, then it jumps. So data tip does have a limited accuracy. But without data tip, if you just simply click, right? So when this one comes, just directly click here. Without the data tip. This one has a lot better accuracy. You can move it much smoother, right? Or as I said, again, you can use the command rlookfind. And rlookfind is a nice one, but first you have to have rlocus. So you have to have first rlocus, then click here, and then if you know where you are clicking, let's say here, then it tells you that that is the gain, right? That is the gain, and the poles, as you can see here, they are very close to what? Negative 0.5, and my gain is very close to 6.01. So these are different commands for doing it in MATLAB. Now, so I guess we have answered most of the things in this problem. We draw it. We found for what range of k the system is stable or not. We found the k value that gives a sigma of negative 0.5 to the poles. The only thing maybe we haven't answered is for what range of k the system is underdamped or overdamped. So we have to talk about this one. So if I go back and look at this, for what range does the system show underdamped or overdamped, right? So if I have when is it that system is underdamped? So I have 3 poles. Each pole corresponds to an exponential in the time domain. And if these poles have what? An imaginary component, then they are corresponding to oscillations with damping, which is underdamped. So when is it that I have underdamped behavior? When I have poles with non-zero imaginary parts, right? Like the beginning system, which has 1 pole here and 2 here. This one gives a constant, and those 2 will provide a underdamped behavior. But if I change k, let's say bring k all the way to this 20, even if I make it very close to 20, 19 point something, where are the poles? So one of them is here, one of them is here, and one of them is probably somewhere there, right? And this term is always a negative exponential, so that term would go away completely, and that is a decaying exponential. But these 2 terms, they will always be what? They will always, because they are non-zero imaginary, they would always show oscillatory behavior. So when you combine them all together, still the system shows underdamped behavior, oscillations. Now, the only case that you can have pure overdamped behavior or critically damped is when, as I said, all of the poles are on the imaginary axis, on the real axis, no imaginary. So for what k value can I get all 3 poles, all of them on the real axis? Is such a thing possible? And the only scenario that might be possible is for some value of k that this green comes down to here, this red comes down to there, and the blue is still not up there. So the first thing is I need to find the k values for this point and that point. Let's do that. So see the k values at the breakaway points, although I guess I found them, right? Because if we go back, I remember I did that. So where was it? I found both of them positive. 7, 6, 5, yes, these two. So the one at -1 is 2, the one at -5/3 is 1.85, okay? So the k here is 2, the k here is 1.85. Let me use a text arrow and show it to you here. So here, insert text box. So here the k is 2. Right? Then I have k of 1.85 here. And I need an arrow. Which is at this point. Right, and then we know at the original locations k is 0, correct? So I can add one more if you want. So the k at this point, let me use the box. So here the k is 0, right? And let me use an arrow. So at the original points, k here is 0, and then at here is also 0, and at here it is also 0. So what happens? So until I am at between 0 to 185, the dominant poles have not reached here. So they are still what? They are still having some imaginary part and underdamped behavior. And this guy has not reached here yet because k is 1.85, so the pole, this pole moves all the way from here to let's say when you make it a little less than 1.85, you are looking at maybe, if I use an ellipse, so one of your poles could be here, right? That's this guy that moves all the way to here, and then the other ones are very close to the imaginary axis. So it's like here, and the other one is like here. Okay. Let me move this away so that you can see better. So this is for a k, these three guys are for a k a little less than 1.85. Still, one of them is decaying, the two others are showing oscillations, so still system is underdamped. Now, when k is between 1.85 and 2, what happens? These two will now move forward, will pass this point, this one still on the imaginary axis. So what happens is this one moves forward like here, and then these two, this green one now comes down to here, right? It follows the green line, and this red one is now following the red branch, so it comes here. And for that case, all three of the poles are on the real axis, so It's just a combination of decaying exponentials, and so it's overdamped. Okay? And once I pass 2, although this green one just keeps being a real forever, this red one comes all the way to this point, okay? So between 1.85 and 2, it reaches itself to here. And then after 2, now this one will jump on the red area, and this one will go on the blue area. So now you have your poles here, 2 of them. The complex conjugate will go here and here, but the green one still what? On the real axis, but those 2 poles will create oscillation and underdamped behavior again. So the answer is, if we want to put everything together for this example, is for stability, K ought to be between 0 and 20. For overdamped behavior, K has to be between 1.85 and 2. But if I want underdamped, then K is either between 0 to 1.85 or between what? 2 and 20. And if I want a sigma of negative 0.5, then the K value has to be 6.01. Okay, so these are the answers to this question that we just went over. Finally, let's see. Okay, 2 more cases to look at before we finish this long lecture. And one of them is, what if the system is non-minimum phase? And the other is, what if the feedback is positive here? So this H is positive, and so the characteristic is 1 minus GH. So first, non-minimum phase. What do I mean by non-minimum phase? So the definition is here. If all the poles and zeros of G times H, if they all lie on the left half of the S-plane, on the left side of the imaginary axis, then the system is called minimum phase if there is any pole or zero, at least one, that is on the right-hand side of the imaginary axis. We call the system non-minimum phase. Why? Where does phase come from here? So it will be reviewed in chapter 7 when we look at the frequency response of systems. We'll see that the systems with a positive, with a polar zero on the positive side of the imaginary axis, when we look at their phase plot, their phase at higher frequencies is significantly more than a similar system for which the poles and zeros with the same number but on the left side. So for example, if you have a 0 at positive 2 and another system with the 0 at negative 2 and the poles are exactly the same, if you plot their phase plot, you see that the angle, the phase of the system with the 0 on the positive side is significantly more than the system with the 1 on the left side at the higher frequency ranges. So that's why we call the system with all zeros and poles on the left side minimum phase, and the one with any positive or on the right side, we call them non-minimum phase. Okay, so we'll see that in chapter 7. But what happens is when you have any positive pole or zero for G times H, that's going to change the behavior of the root locus compared to a similar system with, again, everything else the same, but the zero or pole, instead of being positive, is negative. For example, if you look at these two here, The system on the left is a non-minimum phase where it has poles at what? At 0 and -1. So both of the systems have poles at, right? P1 is 0 and P2 is -1 for both systems. But this system has 0 at what? Clearly see that is at +2. This system has a 0 at -2. So the system on the left is non-minimum phase, the one on the right is minimum phase, and you might wonder, okay, what's the difference? And you clearly see the difference here, that if we apply the angle condition and the magnitude condition and we find the root locus, although the locations of the poles are the same, the 0 is just displaced, it's gonna make the overall appearance is similar, right? It's like a circle, a part of a circle, and then two parts on the imaginary axis. But if you look at the location of them and the parts on the real axis that belong to the root locus, is kind of like mirror image of each other and a little bit of complement of each other. So if you look, these two circles are kind of like almost, not exactly of course, but quite like one of them on this side, one of them on the other side. But if you look at the parts on the real axis, so what part of the real axis this one have? Between 0 to -1 belongs to our locus and less than -2. But look at this one. Between 0 to 1, -1 belongs to, which is the same as this, but instead of less than -2, it's what? More than +2. So again, it's kind of like a mirror of each other with respect to the imaginary, but not exactly, okay? But it does change the behavior of the system. Now, this is not as important as what if the feedback is positive. That would change a bunch of things. So if this feedback is positive, then your closed loop transfer function is g/1 minus gh. And when you set that 1 minus gh to be 0 and take 1 to the other side, then gh instead of -1 becomes what? +1, right? If you go back to the beginning of this lecture, these are the conditions that gh becomes what? -1. And -1 is what? Magnitude 1, but the angle is what? Pi, or pi plus even integers of pi, right? So the angle is pi, 3 pi, 5 pi, 7 pi, 9 pi, and so on. But here, the magnitude condition is the same. Still, g times h at any point should be 1, but the phase is different, because what is the angle of 1? Right? What is angle of 1? Any number on the right-hand side of the imaginary axis, on the real axis, of course, has an angle of 0, right? So the angle ought to be either 0 or 2 pi or 4 pi or 6 pi or 8 pi. So these are even integers of pi, while in the past we had odd multiples of pi. So because this equation, this top one, is changing, it changes a bunch of things to those different items from 1 to 7, right? So when we drew the root locus, we had several stages that we have to do from 1 all the way to 7. But now some of them would change. Which ones? First, remember I told you in order to find on which part of the real axis the root locus falls, you look at how many total poles and zeros are on the right-hand side of a test point. So if on the right-hand side of any test point on the real axis, there is an odd number, a total odd number of poles and zeros, that point belongs to the root locus. But here it is different, actually. The total number of real poles and zeros to the right of a test point should be what? Should be an even number instead of odd number, right? So if I go back and compare these for you, so let's look at some examples together that makes life easier. Maybe the last one is a good example. So the one on the left and the one on the right, if you look at them, or no, actually, these are different examples. So in each example, the solid is the negative feedback, and right, and the dashed lines are positive feedback. So if I just look at this case here, this last one on the left, so the solids are positive, negative feedback. So here, if I choose a point here, does this belong to the root locus of a negative feedback? The answer is no. Why? Because if I count how many real poles and zeros are to the right hand side of it, as I said, the complex ones don't count. So I have what? 1 and 2. So to the right side of this guy is 2 total poles and zeros, so it does not belong to our locus if the feedback is negative. But if the point is here between the two poles, then to the right side of it there is only 1 total, so it belongs. But exactly opposite of that now, if the feedback is positive, how many total zeros and poles are to the right hand side of this test point? 2, since that's an even number, so that point belongs to what? Root locus of the positive feedback. And so the rest of it too. Now if you see, it's not exactly like complementing each other, but they are quite different, okay? So it can make the behavior of the system quite different. If you look at the cases here for the solid versus dash, it is quite different. So positive versus negative feedback. That's one of the rules that changes. The other one, the angle of the asymptotes. Remember, it was an odd number times pi divided by n minus 1. Now it is again a what? An even number times pi divided by n minus m. And similarly, the angle of arrival and departure, if you remember here, it was 180 minus some of the angles from other poles plus some of the angles from other zeros. It was for a complex pole, and opposite of that, 180 minus some of the angles from other zeros plus some of the angles from other poles. That was the arrival angle at a complex zero, right? So now what happens? Both of these 180s become 0 for a positive feedback. And again, going back, this guy here, which was 2k plus 1 times 180, is now become what? That 1 goes away, so it becomes 2k times 180, or k times what? 360, of course. And the other rule that does change is this one here, which says the total number to the thing is an odd number. Now it has to be an even number. The rest of it stays the same, but these three rules would change if the feedback is positive instead of negative, okay? And that would do the root locus. Now you might wonder what happens in MATLAB. So for example, let's do this example with MATLAB if you don't mind. So if I want to draw the root locus of this system, where that is G and H is 1, and one time I do it assuming that the H feedback is negative, the other one I do it assuming that H feedback is positive. So one time I do it for this, H is 1, so nothing changes. So positive, negative, and that is G. So first time I do it for this is what we have been doing. And the next time I do it for this. Positive, positive. So what's the difference? As I said, the characteristic equation here is 1 plus G times H. H is 1, so it's going to be 1 plus G is equal to 0. In this case, it's going to be 1 minus G times H is equal to 0. So how do I distinguish between these two? Of course, it's like one of them is the same as the other, except for positive g became what? Negative g. So I expect if I plot this one time for this g, I get the top one, but if next time I just add a negative to the numerator, it's going to become what? Negative g, and I can do the same way that I did the top one, except I make the numerator coefficients both negative. Okay, so let's look at them together. So this is what we're going to do. The numerator is 1 and 2, the coefficients of that. Again, we never care about k. The denominator coefficient is 1 and 3 multiplied by 1 to 1. So this is what we do. So let's close this and CLC clear all. So we say, give me the root locus of the numerator was 1 and 2. Denominator is 1, 3, 1, 2, 2. 1, 3, 1, 2, 2. So I use the convolution command. 1, 3, and 1, 2, 2. So 1, 3, and 1, 2, 2. So I first multiply them together, get the resulting polynomial, and then pass that as the denominator, right? So if I do that, that is the root locus of the system. So this is the root locus of the system with negative feedback. Okay, so one branch starts from this pole and keeps going as k increases. One starts from here and keeps going as k increases. One of them starts from this pole and ultimately end up at what? This 0. So here k is infinity. Here k is 0. Here k is 0. As it keeps going is infinity, and the same here. So as you probably notice here, the amount of motion on the branches is not the same. These two, when you change k, you get the same distance away from the original, right, for the same k value. So if you make k from 0 to 2, you probably end up the same distance from the original one. But here, no. It takes this pole to go from -3 to -2 when k changes from what? 0 to infinity. So this pole moves very slowly in response to parameter k. K does not change the location of this pole so significantly, but it does change the location of these poles quite badly. Okay? So this is the case for a negative feedback. Now, if I do a positive feedback, so let's see if it allows me to do a root locus on a new figure. So I use the command figure, and then all I do, I make both of these negative. And I do it, and there we go. So now let's put them side by side so that you can see it. Okay, that is too big. I can make it smaller. So this is one, and this is the other one. Okay, so now you can see them side by side and clearly see that the root locus is quite different. So here, this pole starts from here, goes all the way to 0 only. This one starts here and keep going, and this one will keep going. Okay, so the behavior is completely different just because the sign of the feedback is changed. Again, the one on the left side is what? So if I double click on this guy, let's see if it allows me to change it. No. But if I add a text box, so this is negative feedback, and this one is positive feedback. And here we go. I can see them side by side. Okay. I assume I have covered everything I need to cover for you at the moment for the session on the 20th, which is tomorrow, and I will keep posting the new lectures during the weekend for next week, where we go through the rest of it and dig and lag and lead lag compensators. So this is a quite long chapter, but it gives you a nice review of control topics and complex numbers, I would say. One last thing before you go is if you just got my email, I said anything that you ask me which can relate to everybody in class and it's important, I'm going to post your question and my answer under discussion. So when you go under discussions, you see here is the question that one of you asked, that if I cannot submit my quiz or exam right before the quiz or exam Dropbox closes, right before the end of the time for quiz or exam, can I still email you? And I said, well, I allocated 20 minutes extra to any quiz, okay? So any quiz in class was 20 minutes. Now I'm giving you 40 minutes for each quiz to complete. So I'm giving you like 100% extra time just to submit a picture of your work on Canvas, and that should clearly be more than enough. And for exam, I'm going to give you another extra 45 minutes. So the exam is 2 hours, but I'm giving you extra 45 minutes just to upload your files. So I don't think you should have any problem regarding time, but if for any reason that happens before the quiz or exam time ends, you cannot email me or the graders like 1 hour after it ends. No, before so you see your connection is too slow for uploading on Canvas. For some reason, Canvas does not work properly, not your internet, because if your internet is not going to work well, then you cannot also upload it and email it to me. But if Canvas is not working well, then yes, if it's a quiz, go ahead and email it to Marcus, that's his email, and CC me on that. If it's exam, directly email it to me, okay? And we'll get it and we'll grade it. So I'm trying to accommodate the most and the best that I can and help you to have a good time with this course, although we are not meeting face to face. Okay, have a good weekend, and I'll talk to you in my next lecture.